Hello there, and welcome back to our cozy corner of the universe here on the Snoozing Ideas channel. I'm so glad you've joined me tonight, whether you're winding down after a long day or simply seeking a peaceful transition into dreamland. Take a moment now to settle into your most comfortable position, allowing your shoulders to soften and your breath to find its natural, gentle rhythm. Tonight, we'll be floating among the stars to witness one of the cosmos's most spectacular yet soothing phenomena, supernovas. These magnificent stellar farewells may seem intense, but there's something profoundly calming about understanding how even the grandest stars eventually release their light in one beautiful, final gesture. As you drift toward sleep, we'll explore how these celestial events scatter the very elements that eventually formed our world, and perhaps even you. Let's begin. Supernovas whisper across our galaxy with patient rarity. In a galaxy like our Milky Way, these stellar explosions occur approximately once every 50 years, making them cosmic events of notable scarcity. Astronomers have calculated this frequency by studying the remnants of past supernovas and observing their occurrence in similar galaxies throughout the universe. Yet, despite our advanced monitoring capabilities, we sometimes miss these fleeting cosmic moments when they happen in distant parts of our galaxy, obscured by cosmic dust and stellar nurseries. What other celestial phenomena might we be overlooking in the vastness above? Like rare desert blooms that appear after decades of dormancy, supernovas mark cosmic time with brilliant ephemeral displays that most stars will never witness. A dying star can outshine trillions of others in its final moments. When a supernova erupts, its radiance can exceed the combined light of every other star in its galaxy, creating a brilliant cosmic farewell that lasts for several weeks. This extraordinary luminosity comes from the massive energy released when the star's core collapses or undergoes runaway nuclear fusion. The explosion generates enough light to be visible across immense cosmic distances, broadcasting the star's demise far into the universe. Like a single candle that somehow illuminates an entire forest, the supernova burns with impossible brightness, telling a story of transformation where ending becomes spectacle. The calcium in your bones once burned inside ancient stars. Many elements essential for life. The calcium strengthening our skeleton, the iron carrying oxygen in our blood, the phosphorus in our DNA, were created in the extreme conditions found in dying stars. These elements form through nuclear fusion as massive stars burn through their fuel, and especially during the cataclysmic supernova explosion that marks their end. After the explosion, these life-building elements scatter across space, eventually finding their way into new solar systems and planets. Within us are atoms forged in stellar furnaces that existed before our sun was born, connecting our bodies to cosmic events billions of years in the past. Some stellar explosions become visible to human eyes despite occurring thousands of light years away. These rare supernovas appear as new stars in familiar constellations, bright enough to see without telescopes, even across vast cosmic distances. Historical records from cultures worldwide document these sudden celestial visitors, with some becoming bright enough to see during daylight. The light reaching us has traveled so long that we're witnessing events from the distant past, seeing stars as they were when their light began its journey toward Earth. Could ancient observers have understood they were watching stellar deaths? These momentary windows into cosmic catastrophe connect us to both the universe's vastness and our ancestors, who looked up in wonder at the same unexpected lights. The Crab Nebula expands through space like a cosmic ripple. This beautiful structure, the remnant of a supernova Chinese astronomers observed in 1054 CE, continues to expand at approximately 1,500 kilometers per second. Modern telescopes reveal a complex shell of gas and dust, illuminated by a rapidly spinning neutron star at its center, the dense corpse of the original star. Particles in the nebula move outward in all directions, carrying newly formed elements into interstellar space. Like the spreading rings from a stone dropped in still water, this nebula extends the star's influence far beyond its original boundaries. White dwarf stars sometimes consume their companions until they self-destruct. In certain binary star systems, a dense white dwarf, a stellar remnant about the size of Earth, but with the mass approaching that of our Sun, gradually pulls material from its partner star. This stellar vampirism continues until the white dwarf reaches approximately 1.4 times the Sun's mass, a critical threshold called the Chandrasekhar limit. At this precise point, the pressure triggers runaway nuclear fusion that consumes the entire star in seconds. These precision explosions follow identical patterns, making them cosmically reliable, like timekeepers of the universe. Type Ia supernovas serve as cosmic measuring sticks across the universe. These particular stellar explosions always release nearly identical amounts of energy, making their actual brightness remarkably consistent. Astronomers leverage this predictable luminosity to calculate how far away distant galaxies are by comparing how bright these supernovas appear to how bright they should be. This technique helped reveal the universe's accelerating expansion and the existence of dark energy. Though questions remain about what might cause slight variations in their behavior, these stellar standard candles continue guiding our understanding of cosmic distances. Like identical lighthouses placed across an infinite ocean, they help us map the universe's vast geography. Supernova shockwaves race through space faster than anything on Earth could comprehend. Following the initial explosion, these walls of energy and matter travel at speeds reaching 30,000 kilometers per second, a velocity that would circle our planet in less than 2 seconds. These rapidly expanding shells compress gas clouds they encounter, heating them to millions of degrees and causing them to glow in various wavelengths. The energy carried by these cosmic tsunamis can influence regions hundreds of light years across. Like silent thunder rolling through the cosmos, these invisible waves reshape everything in their path. Automated telescopes discover hundreds of distant supernovas while we sleep. Approximately 300 supernovas are detected each year in faraway galaxies by robotic observatories tirelessly scanning the night sky. These automated systems compare images taken on different nights, identifying new points of light that weren't visible before. Many of these cosmic explosions occurred billions of years ago, their light only now reaching our instruments. The light from these ancient deaths travels across nearly unfathomable distances, carrying information from times long before Earth existed. Have we glimpsed supernovas from galaxies that no longer exist? Like messengers from the cosmic past, these faint signals connect us to the universe's distant history. A massive star's core collapses with unimaginable speed during its final moments. In less than a single second, the iron core of a dying star, a region larger than Earth, implodes due to the overwhelming force of gravity. This sudden compression creates pressures and temperatures that exceed those found anywhere else in the current universe. The core's density increases until atomic nuclei touch, creating a neutron star, or, in more massive stars, a black hole. From this catastrophic compression springs the energy for the supernova explosion. like a cosmic heartbeat suddenly arrested and then released. This moment transitions a star from life to legacy. Some supernova remnants continue glowing for millennia after the initial explosion fades away. These structures, visible primarily in X-ray wavelengths invisible to human eyes, persist for thousands of years as evidence of ancient stellar deaths. The high-energy radiation comes from gas heated to millions of degrees by the ongoing shock wave and from particles accelerated by the remnants' magnetic fields. Astronomers study these cosmic fossils to understand how supernovas affect their surroundings and distribute elements throughout galaxies. Like ancient ruins that outlast their builders, these ghostly remnants testify to stars that existed long before recorded history. Betelgeuse glows with the uncertain promise of future brilliance. This red supergiant star, visible as the shoulder of Orion, lies approximately 640 light-years from Earth and ranks among our nearest supernova candidates. Its enormous size, if placed at the center of our solar system, it would extend beyond Jupiter's orbit. And advanced age suggests it will explode relatively soon in astronomical terms. When it eventually does, the supernova will be visible during daylight, casting shadows at night, though still too distant to harm Earth. Like a timer counting down to an unknown zero, Betelgeuse holds the potential for the most spectacular celestial display in human history. Neutrinos escape a supernova before its light begins to shine. These nearly massless particles interact so weakly with matter that they pass through the entire Earth with virtually no collisions. During a supernova, an incredible burst of neutrinos carries away 99% of the explosion's energy, racing outward at nearly the speed of light. Detectors on Earth caught about 20 neutrinos from supernova 1987A before any visible light reached us, providing the first early warning of a stellar explosion. Like invisible messengers slipping through cosmic walls, these ghost particles reveal the hidden first moments of stellar death. Neutron stars form with magnetic fields of almost incomprehensible strength. Many supernova explosions leave behind these ultra-dense remnants with magnetic fields trillion times stronger than Earth's. These fields can be so intense they distort the very structure of atoms nearby and channel particles into beams that sweep through space like cosmic lighthouses. When these beams cross our line of sight, we observe them as rapidly pulsing radio sources called pulsars. The physics of how these magnetic fields form remains partly mysterious, with questions about how they achieve such extraordinary strengths. Like microscopic mountains that somehow grow taller than planets, these fields defy our intuitions about what nature allows. The expanding shell of a supernova can trigger the birth of new stars. As the shock wave travels outward, it compresses gas clouds it encounters, increasing their density until gravity takes over and initiates star formation. This cosmic cycle of death-creating life plays out across our galaxy, with some star clusters showing evidence of having been triggered by ancient supernovas. Astronomers believe our own sun may be several generations removed from the original stars that formed after the Big Bang. Like forest fires that release seeds requiring extreme heat to germinate, these stellar explosions ensure the galaxy continues renewing itself through destruction. A star must achieve significant mass to die as a supernova. Type 2 supernovas require progenitor stars with at least 8 times the mass of our Sun, a threshold that separates stars destined for dramatic endings from those like our Sun, which will eventually fade as white dwarfs. These massive stars burn through their nuclear fuel much more quickly, living just millions rather than billions of years. Their greater gravitational pressure allows fusion of heavier elements until an iron core forms. Like cosmic weight limits determining different destinies, this mass threshold divides stars between quiet and spectacular ends. A typical supernova releases energy almost beyond comprehension. The explosion generates energy equivalent to what our Sun will produce over its entire 10 billion-year lifespan, all concentrated into just a few weeks. This extraordinary power output briefly makes the dying star one of the most energetic objects in the universe. The temperatures reach billions of degrees, creating conditions that forge new elements and accelerate particles to near light speed. Like a lifetime of whispers suddenly compressed into one deafening shout, the supernova represents concentrated stellar potential released in a singular moment. Superbubbles expand through interstellar space like cosmic breaths. These enormous cavities, spanning hundreds of light years, form when multiple supernovas occur in the same region, their shockwaves merging and reinforcing each other. The combined energy sweeps up interstellar gas into dense shells while leaving low-density regions inside. These structures influence galaxy evolution, potentially triggering or preventing star formation in different regions. What cosmic stories are written in these ancient void patterns? Like invisible architecture shaping the galaxy's development, these bubbles demonstrate how stellar deaths collectively reshape their cosmic neighborhood. The iron in your blood was forged in stellar catastrophe. Elements heavier than iron, including cobalt and nickel, require the extreme conditions found only in supernova explosions to form. Unlike lighter elements that generate energy when fused in living stars, iron fusion consumes energy, marking a terminal point in stellar evolution. When a massive star's core fills with iron, its energy production falters, leading to collapse and explosion. This violent process creates the pressure and neutron flux necessary to build heavier elements. Like alchemical laboratories operating at cosmic scales, supernovas transmute simple elements into complex ones that eventually find their way into planets and living beings. Hypernovas shine with extraordinary intensity among stellar explosions. These rare events release up to 100 times more energy than typical supernovas, often associated with the formation of black holes and gamma-ray bursts. They result from the collapse of extremely massive, rapidly rotating stars, whose deaths are more catastrophic than ordinary supernovas. The energy released briefly outshines entire galaxies, making them visible across billions of light years. Scientists continue studying these extreme events to understand the upper limits of stellar explosions and their role in cosmic evolution. Like cosmic maximalists refusing quiet endings, these stars transform their demise into universe-spanning announcements. The Vela supernova remnant stretches across our sky with ancient presence. This 11,000-year-old structure spans 8 degrees of sky as seen from Earth, 16 times wider than the full moon. Despite being partially visible to the naked eye, as faint nebulosity in the southern constellation Vela, most observers never recognize this enormous remnant of cosmic violence. Modern telescopes reveal its complex structure of shock-heated gas filaments still expanding from an explosion that likely appeared brighter than Venus to early humans. Like grand ruins, visible only when we know where to look, this remnant demonstrates how cosmic history quietly surrounds us. Stars often signal their approaching end through extended farewells. Many supernova progenitors undergo substantial mass loss for thousands of years before their final explosion, ejecting shells of material that create complex surroundings. These outflows can form rings, bubbles, or asymmetrical clouds that the later supernova shockwave will encounter, creating distinctive light patterns. This pre-explosion activity provides astronomers with clues about the star's final evolutionary stages. Like leaves falling before winter arrives, these stellar exhalations announce transformations still to come. The brilliance of a Type Ia supernova exceeds our Sun by factors difficult to comprehend. At maximum brightness, these stellar explosions reach approximately 5 billion times the luminosity of our Sun, making them briefly comparable to small galaxies, despite being just single stellar events. This extraordinary energy output comes from the radioactive decay of nickel-56 produced in the explosion, which gradually transforms into cobalt and then stable iron. The light curve, how the brightness changes over time, follows predictable patterns, rising quickly and then falling over weeks as radioactive elements decay. Like cosmic standard candles, their reliable brightness has helped reveal the universe's accelerating expansion. Supernova shockwaves create some of the hottest temperatures in today's universe. As the expanding blast wave collides with surrounding gas, it creates conditions where temperatures exceed 10 million degrees Celsius. This extreme heat causes the gas to emit X-rays that specialized space telescopes can detect and map. The temperature gradients across supernova remnants help astronomers understand how energy transfers through interstellar space and how different elements respond to shock heating. Scientists continue studying these temperature patterns to better understand the physical processes involved. Like invisible fever dreams expanding through space, these thermal gradients write complex stories in wavelengths beyond human sight. Cassiopeia. A contains knots of material racing outward at incredible speeds. This relatively young supernova remnant, only about 340 years old, shows complex structures of ejected material moving at approximately 5,000 kilometers per second. Detailed observations reveal over 10,000 distinct knots of gas enriched with different elements, arranged in overlapping layers that tell the story of the original star's structure. These high-speed fragments carry newly created elements outward, where they will eventually mix with interstellar gas. What cosmic destinations await these stellar fragments? Like seeds scattered by an exploding flower, these knots distribute the star's legacy across vast distances. The last observed supernova in our galaxy occurred over 4 centuries ago. In 1604, a new star appeared in the constellation Ophiuchus, bright enough to see during daylight for several weeks. Johannes Kepler meticulously documented this cosmic visitor, not knowing he was witnessing the death throes of a distant star. Modern astronomers find this absence of observed galactic supernovas surprising, suggesting that several may have occurred in parts of the galaxy obscured from Earth by cosmic dust. Radio telescopes and other instruments continue monitoring for signs of recent explosions hidden from optical view. Like celestial rarities, we await with patient telescopes. These events remind us of the galaxy's ongoing evolution. Massive stars create elements through progressive stages of nuclear fusion. The process of nucleosynthesis builds increasingly heavy elements from hydrogen to helium, then carbon, neon, oxygen, silicon, and finally iron. Each fusion stage occurs in concentric shells within the star, with temperature and pressure increasing toward the center. When iron accumulates in the core, fusion can no longer produce energy, leading to collapse and explosion. The elements created in these stellar furnaces eventually become distributed throughout the galaxy. Like cosmic factories gradually producing more complex materials, these stars transform simple hydrogen into the building blocks of planets and life. Some supernova remnants remain visible for 100 millennia after their initial explosion. These ancient structures interact with surrounding molecular clouds, creating complex patterns as fast-moving shockwaves encounter dense interstellar material. The interaction can trigger star formation, compress magnetic fields, and accelerate cosmic rays to nearly the speed of light. Radio telescopes reveal these interactions through distinctive emission patterns long after the visible light has faded. Have ancient supernovas shaped the very environment where our solar system formed? Like ripples in a cosmic pond that continue long after the stone has sunk, these remnants influence galactic evolution across vast timescales. The majority of a supernova's energy escapes human detection entirely. During the collapse phase of a core collapse supernova, approximately 99% of the total energy releases as neutrinos, nearly massless particles that interact so weakly with matter, they pass through entire planets unimpeded. These neutrinos carry away crucial information about the explosion's first moments and the transformation of the star's core. Only specialized detectors, buried deep underground, shielded from cosmic rays, can capture the rare interactions of these elusive particles. Like whispered secrets from dying stars, these neutrino bursts contain information about physical processes impossible to recreate on Earth. Ancient galaxies sometimes host unexpected stellar explosions. Many Type Ia supernovas occur in elliptical galaxies, where star formation ceased billions of years ago, raising questions about their origin. These galaxies contain primarily older stars that should have exploded long ago if they were massive enough for a supernova. Astronomers believe these delayed explosions come from white dwarfs, gradually accumulating matter from companion stars until reaching critical mass. The time required for this process explains why these supernovas continue appearing in otherwise dormant stellar populations. Like delayed echoes from a galaxy's youth, these explosions connect ancient star formation to contemporary cosmic events. Tycho's supernova brought celestial change to Renaissance skies. The 1572 supernova, visible during daylight for several weeks, challenged the prevailing Aristotelian belief in an unchanging celestial realm. Danish astronomer Tycho Brahe's precise measurements confirmed this new star existed beyond the moon, proving changes could occur in the supposedly perfect heavens. This realization contributed to the scientific revolution that transformed human understanding of the cosmos. Modern observations of the remnant reveal an expanding shell of superheated gas still traveling outward at supersonic speeds. Like a single observation that rewrites human knowledge, this supernova illuminated not just the sky, but scientific thought itself. Supernovas accelerate particles to energies approaching those in our most powerful machines. The rapidly expanding shock waves generate intense magnetic fields that can accelerate cosmic ray particles, primarily protons and atomic nuclei, to energies approaching those in particle accelerators. These natural cosmic accelerators propel particles to near light speed, sending them on journeys lasting millions of years through interstellar space. Some eventually reach Earth's atmosphere, creating cascades of secondary particles detected by ground-based observatories. Might some particles passing through your body right now have begun their journey in ancient stellar explosions? Like invisible messengers from distant catastrophes, these particles connect us physically to cosmic events. 1,000-year-old stellar explosion united observers across human cultures. The SN 3006 supernova appeared as the brightest stellar event in recorded history, documented by astronomers in China, Japan, Europe, and throughout the Arab world. Contemporary accounts described it as shining with the brightness of the quarter moon and visible during daylight for weeks. The explosion occurred approximately 7,200 light-years away, meaning observers witnessed light that began its journey during Earth's early medieval period. Modern telescopes reveal an almost perfectly circular remnant, still expanding into interstellar space. Like a moment of shared wonder, transcending cultural boundaries, this cosmic event briefly united diverse human experiences across the medieval world. Many stars destined for spectacular ends live their lives in cosmic partnerships. Numerous supernova progenitors exist in binary systems where material transfers between the stars, significantly affecting how they evolve and eventually explode. This stellar dance changes the composition and rotation rate of both partners, potentially determining whether the explosion creates a neutron star or black hole. The companion star may survive the explosion, continuing as a widowed stellar remnant with peculiar properties that astronomers can identify. In some cases, the companion receives enough kinetic energy to escape the system entirely, becoming a hypervelocity star traveling through the galaxy. Like relationships that fundamentally change both partners, these binary interactions create unique cosmic stories. Light echoes allow astronomers to witness supernovas long after their initial brilliance fades. The Hubble Space Telescope has observed supernova light reflecting off dust clouds years after the original explosion, giving scientists multiple perspectives on the same event. These echoes, traveling slightly longer paths to reach Earth, effectively let astronomers observe the supernova from different angles and at different times. Studying these delayed reflections provides information about both the explosion itself and the structure of surrounding dust clouds. Like cosmic time capsules preserving moments of stellar transformation, these echoes extend our window of observation into events long considered complete. White dwarfs breathe in helium, then exhale in brilliant flashes of light. Some of these stellar remnants slowly accumulate helium from nearby companion stars, gathering this light element layer by layer. Once enough helium collects on their surface, it suddenly ignites in a thermonuclear flash visible across vast distances. Unlike the single catastrophic explosion that ends the star's existence, these helium flashes occur repeatedly, like a cosmic heartbeat. The cycle continues as long as the companion star provides material, creating a rhythm of accumulation and release that can persist for millions of years. Like breath held and then released, these periodic ignitions mark the quiet passage of stellar time. The Sedov-Taylor phase unfolds like a slow cosmic breath across millennia. During this intermediate stage of supernova expansion, the remnant has swept up more interstellar material than was originally ejected in the explosion. The physics simplifies to a beautiful mathematical relationship between energy, density, and time. This phase can persist for tens of thousands of years, with the shock front gradually slowing as it pushes against the surrounding medium. Energy disperses across an ever-widening sphere, fading but expanding. Like a whisper that spreads through a silent room, the star's final message travels outward, touching everything in its path with diminishing but persistent force. Eventually, all stellar catastrophes fade into cosmic anonymity. After traveling outward for 50,000 to 100,000 years, many supernova remnants become indistinguishable from the general interstellar medium. Their once defined boundaries blur as shock waves dissipate and temperatures cool to match the surrounding space. Elements created in the explosion mix with the galactic medium, becoming part of the raw material for future stars and planets. The distinctive signatures that identified the region as a supernova remnant gradually disappear. Like footprints washing away on a shore, these ancient explosions ultimately surrender their identity to become part of the cosmic whole. Our coronae borealis stars vanish and reappear like cosmic ghosts. These unusual variables occasionally fade from visibility when carbon dust forms in their atmospheres, then brighten again when the dust disperses. Astronomers believe they may represent a rare class of supernova progenitors, formed perhaps by the merger of two white dwarfs. Their atmospheres show almost no hydrogen, but are rich with carbon, giving them distinctive spectral signatures. Their exact evolutionary path remains uncertain, with several competing theories attempting to explain their unusual properties. Are they failed supernovas, or stars preparing for a final explosion? Their periodic disappearances mirror their mysterious nature. Stars playing hide-and-seek across cosmic time. Some dying stars become entangled in their own expelled breath. Type the tune supernovas reveal narrow emission lines in their spectra, indicating interaction between the explosion and dense material the star released before its death. This stellar material, expelled during the star's final unstable years, forms a cocoon that the supernova shockwave later collides with. The interaction creates distinctive light patterns that astronomers can recognize across vast distances. This cosmic conversation between a star's past and its violent end tells stories about the progenitor's final moments. Like letters written to the future, these spectral lines preserve messages from stars that no longer exist. Across interstellar space, our nearest cosmic neighbor offered us a gift. In 1987, the Large Magellanic Cloud, a satellite galaxy of our Milky Way, hosted Supernova 1987A, the closest observed supernova of modern times. Light from this stellar death reached Earth after traveling 168,000 light-years through space. For the first time, astronomers detected neutrinos from a supernova before seeing its visible light, confirming theoretical models of stellar collapse. The explosion originated from a blue supergiant, surprising scientists who expected a red supergiant progenitor. Like a rare opportunity to witness cosmic transformation up close, this nearby supernova continues teaching us about stellar evolution decades after its first light reached Earth. Artificial minds now watch the sky for dying stars. Modern supernova searches employ machine learning algorithms to identify candidates in the vast flood of data from automated sky surveys. These digital sentinels sift through millions of images nightly, recognizing patterns human eyes might miss. They learn to distinguish the brief flare of a distant supernova from other transient events like asteroids, variable stars, or instrument artifacts. The algorithms improve with each discovery, becoming more sensitive to the subtle signatures of stellar death. Like attentive guardians of cosmic change, these artificial astronomers ensure we notice when stars bid their final farewell, however distant they may be. A cosmic threshold divides stars between different destinies. The Chandrasekhar limit, 1.4 times the mass of our Sun, defines the maximum possible mass of a white dwarf star. Beyond this precise boundary, electron degeneracy pressure can no longer support the star against its own gravity. This mathematical limit, calculated by physicist Subrahmanyan Chandrasekhar in 1930, predicts exactly when a white dwarf will collapse and explode as a Type Ia supernova. The consistency of this threshold helps explain why these explosions release such uniform energy. Like a line drawn across the cosmos, this mass limit separates stars that will fade quietly from those destined for spectacular transformation. Some stellar remnants carve arcs through interstellar space. When supernova remnants travel through the galaxy at high speeds relative to their surroundings, they create bow shocks, curved fronts of compressed gas, similar to waves before a ship's bow. These structures form as the expanding remnant collides with interstellar material while moving through it. The resulting arc-shaped compression zones can span light years, glowing in radio and X-ray emissions. These cosmic waves tell astronomers about both the remnant and the medium it travels through. Like ships leaving wakes in an invisible ocean, these stellar remains draw momentary patterns across the face of the galaxy. The Kepler remnant continues its slow expansion 4 centuries after Johannes Kepler first glimpsed its birth. This supernova, observed in 1604, was the last to be seen in our galaxy with the naked eye. Today, sophisticated space telescopes reveal complex structures of hot gas still moving outward from the explosion point. Different elements within the remnant emit light at various wavelengths, creating a multicolored portrait of stellar death. The ejected material encounters varying densities in the surrounding medium, creating asymmetrical patterns of expansion. Like ripples in a complex medium, the star's final message continues propagating through space, growing fainter but wider with each passing year. Some stars shed their outer layers before their final performance. Many Type Ib and EC supernovas originate from massive stars that lost their hydrogen envelopes, either stripped away by stellar winds or transferred to companion stars. Without these outer hydrogen layers, the explosions produce distinctive spectral signatures that astronomers can identify across vast distances. These stripped envelope supernovas reveal the complex evolutionary pathways massive stars may follow before their end. What cosmic forces remove a star's outer garments before its final act? Like performers changing costumes before their final scene, these stars transform themselves before delivering their concluding cosmic display. Supernova remnants create some of the hottest environments in today's universe. The shock heating in these expanding structures strips electrons from atoms, creating plasmas with temperatures reaching millions of degrees. This extreme heating causes the gas to emit across the electromagnetic spectrum, from radio waves to gamma rays. Different elements produce distinctive emission lines, allowing astronomers to map the distribution of materials created in the explosion. These temperature extremes exist in delicate balance, with cooling processes that will eventually return the material to ambient conditions. Like fever dreams spreading through interstellar space, these thermal excitations gradually fade as energy disperses across expanding volumes. In the early universe, stars died in ways we no longer witness. Some pair instability supernovas may have occurred from massive stars exceeding 140 solar masses, giants that could form only in the pristine conditions of the early cosmos. In these extraordinary stars, energy from gamma rays created pairs of electrons and positrons, reducing pressure support and triggering collapse and explosive burning. The resulting explosions would have been vastly more energetic than any supernovas we observe today, completely disrupting the star without leaving any remnant. Like lost languages from civilizations long vanished, these ancient stellar endings leave only faint traces for us to reconstruct their stories. Cosmic dust glows with the warmth of ancient explosions. The Spitzer Space Telescope detected warm dust in supernova remnants, heated by shock waves still moving outward long after the initial explosion. This dust containing silicates, carbon, and other materials, plays a crucial role in galaxy evolution and planet formation. Some of it forms in the cooling ejecta as elements combine in the aftermath of the explosion. Studying this dust reveals how supernovas contribute to the cosmic cycle of material that eventually forms new stars and planetary systems. Like embers still warm from fires long extinguished, these dust particles carry thermal signatures of transformative cosmic events. Neutron stars continue to shape space long after their violent births. Many supernova explosions leave behind pulsar wind nebulae, regions of energized particles and magnetic fields powered by rapidly rotating neutron stars at their centers. These stellar remnants, spinning up to hundreds of times per second, generate powerful electromagnetic fields that accelerate particles to near light speed. The resulting nebulae often display complex structures, filaments, and jets, visible across multiple wavelengths. The Crab Nebula contains perhaps the most famous example, where energy from the pulsar continues shaping the remnant almost a millennium after the initial explosion. Like cosmic lighthouses spinning in the dark, these pulsars illuminate their surroundings with rhythmic energy. Light transforms into higher energies within supernova remnants. The process of inverse Compton scattering occurs when low-energy photons collide with high-energy electrons, accelerated by the remnant's shock waves. These collisions boost the photons to gamma-ray energies, creating emission that specialized space telescopes can detect. This process reveals the population of energetic particles within the remnant and helps astronomers understand how cosmic rays are accelerated. The remnant becomes a natural particle accelerator vastly larger than anything humans could build. Like cosmic alchemists transmuting elements, these ancient explosions continue transforming energy from one form to another across thousands of years. Some stellar explosions change their appearance as we watch. Type 2b supernovas transition from hydrogen-rich to hydrogen-poor spectra during their evolution, revealing layers of different composition as the explosion unfolds. Initially, the spectra show hydrogen lines typical of Type 2b. Better nosepods, but these fade within weeks as the outer layers disperse, exposing helium-rich material beneath. This evolution suggests the progenitor had only a thin hydrogen envelope remaining when it exploded. The star's layered history becomes briefly visible as the explosion peels it away. Like a book whose pages turn themselves, these transitional supernovas reveal their internal structure through temporal changes in their light. The highest energy light in the universe sometimes originates from stellar remains. The Fermi Gamma Ray Space Telescope has detected GeV emission, billions of electron volts, from several supernova remnants. These gamma rays form when accelerated particles interact with surrounding material or magnetic fields. The emission patterns help astronomers map how cosmic rays are produced and confined within remnants. Different acceleration mechanisms create distinctive gamma-ray signatures that reveal the remnant's structure and dynamics. Could some cosmic rays reaching Earth have originated in these ancient stellar explosions, like invisible energetic ghosts? These high-energy particles and photons carry the supernova's influence across interstellar distances. Stars often change color in their twilight years. Many supernova progenitors undergo blue supergiant or red supergiant phases before their final explosion. These color changes reflect fundamental transformations in the star's structure and energy production as it exhausts its nuclear fuel. Red supergiants expand to enormous sizes, while blue supergiants remain more compact, but intensely hot. The particular evolutionary path affects the resulting supernova's characteristics and remnant. Betelgeuse currently exists as a red supergiant, while the progenitor of SN 1987A was a blue supergiant. Like autumn leaves displaying brilliant colors before falling, these giant stars signal their impending transformation through visible changes. Invisible force fields grow stronger amid stellar destruction. The magnetic field amplification in supernova shocks can increase field strength by factors of 100 or more. These enhanced fields arise from turbulence and instabilities as the shockwave interacts with interstellar material. The amplified fields help accelerate charged particles to high energies, contributing to cosmic ray production. They also affect the remnant's evolution and appearance across different wavelengths. Though invisible to our eyes, these magnetic structures shape the visible features we observe. Like unseen hands sculpting cosmic clay, these fields guide the movement of charged particles, creating patterns visible only through their effects. Not every stellar outburst marks a final goodbye. Some supernova imposters, like the massive star Eta Carinae, undergo spectacular eruptions without actually exploding. These luminous blue variables can briefly outshine most stars in their galaxy during outbursts, ejecting enormous shells of material. The great eruption of Eta Carinae in the 1840s made it the second brightest star in the sky, despite its distance of 7,500 light-years. Unlike true supernovas, the central star survives these episodes, sometimes repeating the cycle multiple times. Like false endings in a cosmic drama, these imposters remind us that stellar evolution follows many paths, not all leading to immediate destruction. X-rays trace invisible patterns of stellar dissolution. The X-ray emission from supernova remnants reveals the distribution of hot-shocked gas, mapping regions too energetic to emit visible light. These high-energy photons originate from plasma heated to millions of degrees by the ongoing shock wave. Different elements in the ejecta produce distinctive X-ray signatures, allowing astronomers to map the distribution of materials created in the explosion. The resulting images show complex structures, shells, filaments, and clumps that reveal the remnant's evolution. Like thermal photographs showing what eyes cannot see, these X-ray portraits expose the hidden energy landscapes of ancient stellar remains. Some cosmic flashes defy our categories of stellar death. Many calcium-rich transients represent a distinct class of peculiar supernova-like explosions that produce unusually high amounts of calcium relative to other elements. These events often occur far from obvious host galaxies, raising questions about their progenitors. Some theories suggest they result from white dwarf mergers or helium detonations on white dwarf surfaces. Their spectra evolve quickly to show strong calcium emission while lacking expected features of typical supernovas. What strange stellar alchemy creates these calcium factories in space? Like cosmic anomalies waiting to be understood, these transients expand our understanding of the many ways stars can end their lives. Star birth and star death maintain a cosmic equilibrium. The supernova rate in star-forming galaxies correlates strongly with the galaxy's infrared luminosity, which traces the formation rate of massive stars. This relationship creates a balance. Galaxies forming more stars will experience more supernovas, which in turn trigger the formation of new stars. The metal-enriched material ejected by supernovas becomes incorporated into new stellar systems, increasing their complexity. This cycle has continued since the earliest generations of stars, gradually enriching the universe with heavier elements. Like breath moving in and out, this rhythm of creation and destruction shapes the chemical evolution of galaxies. Light curves tell stories about how stars unravel. Some type YL supernovas show linear decline in their light curves over several months, distinguishing them from plateau-type events that maintain brightness longer. This steady fading reflects the progenitor star's structure, particularly its hydrogen envelope, and how the explosion energy propagates through it. The slope of this decline contains information about the star's mass, composition, and the explosion dynamics. Astronomers read these light curves like cosmic diaries, extracting narratives of stellar evolution from changes in brightness. Like the gradually dimming embers of a once bright fire, these fading light curves mark the slow dissipation of energy released in a star's final moment. Individual fragments of stellar memory drift through space in silence. The Chandra X-ray Observatory has resolved distinct knots and filaments within nearby supernova remnants, each representing a piece of the original star traveling on its own trajectory. These fragments contain different elements created during the star's life and death, preserving a record of nuclear processes that occurred before the explosion. Some knots show evidence of radioactive decay of unstable isotopes, allowing astronomers to trace their origins within the progenitor. Like scattered pages from a cosmic autobiography, these fragments carry portions of the star's history outward into the interstellar medium. The afterglow of stellar death follows predictable patterns of decay. Many supernova light curves can be modeled using the radioactive decay chains of nickel-56, transforming to cobalt-56, and finally, to stable iron-56. The energetic particles released during these decays heat the expanding ejector, generating light that follows the characteristic half-lives of these isotopes. This luminosity pattern creates a distinctive signature that astronomers can recognize across vast distances. The amount of radioactive material synthesized in the explosion determines the supernova's peak brightness and how quickly it fades. Like the steady ticking of a cosmic clock, these radioactive elements mark time after a star's ending. Stars sometimes receive cosmic farewell kicks during their final moments. The asymmetry in supernova explosions may explain the high velocities of some neutron stars, which can travel through space at hundreds of kilometers per second. These runaway neutron stars receive their momentum from imbalanced forces during the explosion, sending them in the opposite direction from the majority of ejected material. The exact mechanisms creating this asymmetry remain unclear, though turbulence, rotation, and magnetic fields likely play roles. Like seeds ejected from an exploding pod, these dense stellar remnants carry their compact mass across interstellar distances, their trajectories forever altered by their violent births. Cosmic dust forms in the cooling breath of exploded stars. Some supernova remnants show evidence of dust formation in their ejecta within the first few years after the explosion. As the expanding material cools, atoms condense into microscopic solid particles, silicates, carbon, and metallic compounds. This newly created dust eventually mixes with the interstellar medium, potentially becoming incorporated into new stars and planetary systems. The dust's composition reflects the elements synthesized in the explosion, providing a direct link between supernovas and the materials that form planets. Like cosmic snowflakes crystallizing in the aftermath of stellar winter, these dust particles transform gas into the seeds of future worlds. Swift messengers now carry news of distant stellar deaths. The Swift satellite has enabled rapid follow-up observations of supernovas discovered by ground-based surveys, allowing astronomers to study these events during their earliest stages. Named for its quick response capabilities, this orbital observatory can reorient within minutes to observe new transients across multiple wavelengths. Early observations provide crucial information about the explosion's physics and the progenitor star's properties before the expanding debris obscures them. What secrets hide in these first moments of stellar transformation? Like witnesses arriving at the scene of cosmic events, these quick observations capture ephemeral details that would otherwise be lost. Some stellar farewells linger at the same brightness, as if reluctant to fade away. Many Type TIP supernovas maintain nearly constant brightness for 2 to 3 months due to hydrogen recombination in their expanding envelopes. As the ejected material cools, electrons reunite with protons, releasing energy that sustains the supernova's luminosity despite the expanding surface area. This plateau phase creates a distinctive light curve that astronomers can recognize across vast distances. The duration of this plateau reveals the mass of hydrogen in the progenitor's outer layers. Like a held note in a cosmic symphony, these sustained brightnesses mark a pause in the star's final diminuendo. Stars accelerate invisible messengers to nearly the speed of light. The cosmic ray acceleration efficiency in supernova remnants ranges from 1% to 50% of the explosion energy, converting thermal energy into the kinetic energy of charged particles. These particles spiral around magnetic field lines, gaining energy with each crossing of the shock front. The efficiency varies with the remnant's age, structure, and environment, reaching maximum values during intermediate evolutionary stages. These accelerated particles eventually escape into interstellar space, some eventually reaching Earth. Like energy transformed but never lost, these particles carry the supernova's influence across interstellar distances in a form beyond light. Some stars outshine galaxies in their final moments. Superluminous supernovas reach peak magnitudes 10 to 100 times brighter than normal type Ia events, making them visible across billions of light years. These extreme explosions may derive their extraordinary energy from magnetars, highly magnetized neutron stars spinning hundreds of times per second, or from interaction with dense material ejected before the explosion. Some may result from pair instability mechanisms in very massive stars. What cosmic extremes create these brightest of stellar endings? Like cosmic beacons visible across the observable universe, these rare events push the boundaries of what stellar explosions can achieve. New eyes will soon observe ancient stellar ghosts with unprecedented clarity. The James Webb Space Telescope will observe supernova remnants in infrared wavelengths with resolution and sensitivity far beyond previous instruments. These observations will reveal dust formation, molecular interactions, and faint features previously invisible to astronomers. The telescope's spectroscopic capabilities will identify chemical compositions with new precision, tracking how supernovas contribute to cosmic chemical evolution. What hidden structures and processes await discovery? Like revealing previously invisible ink on cosmic parchment, these observations will uncover aspects of stellar afterlives we have never before witnessed. Automated sentinels maintain constant vigilance over distant galaxies. Many supernova searches now monitor millions of galaxies automatically each night, comparing new images with reference data to detect changes. These robotic systems can discover cosmic explosions within hours of their first light reaching Earth, enabling rapid follow-up observations. The accumulated data from these surveys helps establish rates and distributions of different supernova types across cosmic time. From these patterns emerge clues about galaxy evolution, star formation history, and the changing composition of the universe. Like attentive guardians watching for momentary flashes in the cosmic dark, these systems ensure that few stellar endings go unnoticed or unrecorded. In the quiet dance of stars, sometimes the smallest spark ignites a cosmic farewell. Some Typeia supernovas begin with delicate helium shells surrounding white dwarf stars. When this thin layer ignites, its explosion sends a shockwave inward, triggering a second, more powerful detonation in the carbon-oxygen core. This double detonation mechanism transforms the entire star into expanding light and energy. You, watching the night sky, might someday witness the distant flash from such a moment. Light traveling years to reach your eyes, connecting you to this beautiful complexity. We are the witnesses to these cosmic transformations, our consciousness a mirror in which stellar endings find their meaning. Above our heads, scientists create tiny universes to understand the birth of cosmic dust. Aboard the International Space Station, experiments recreate the conditions found in cooling supernova ejecta, studying how microscopic dust grains form when free from Earth's gravity. These dust particles, silicates, carbon, and metallic compounds, eventually become part of planets and people. The same processes that formed dust in ancient stellar explosions continue in these orbital laboratories, connecting human curiosity to cosmic creation. We reach toward understanding with experiments floating in silence, learning how the materials of our bodies first condensed in the aftermath of stellar deaths. Within ancient star clusters, we read stories of stellar generations touching one another. Many globular clusters, spherical islands of stars orbiting our galaxy, show evidence of multiple stellar populations, some enriched with elements created by the cluster's first supernovas. These ancient explosions seeded their surroundings with heavier elements, which subsequent generations of stars incorporated as they formed. The history of these stellar families is written in their chemistry, preserved for billions of years. You and I share this pattern of inheritance. Our own bodies carry elements passed down through generations of stars, connecting us to cycles of cosmic renewal that began long before Earth existed. The gentle gradient of metals across galaxy disks tells a story of stellar lives given to creation. This metallicity pattern, increasing concentration of elements heavier than helium as we move inward, reflects billions of years of supernova enrichment, more frequent in the crowded galactic center than in the sparse outer regions. Each explosion contributed its unique elemental signature, gradually building the chemical complexity needed for planets and life. We live within the story of cumulative creation, our solar system positioned where enough supernovas had occurred to enable our existence. Your body carries the legacy of this perfect placement, this fortunate abundance of stellar-forged elements. Some stars find their ending through a gentle collapse rather than violent explosion. Intermediate mass stars may undergo electron capture supernovas when their oxygen neon magnesium cores reach a critical density, causing electrons to merge with atomic nuclei in a cascade of quantum surrender. This process triggers collapse without the extreme energies of more massive stars. There is beauty in this quieter transformation, this acceptance of gravitational inevitability. Like a whispered farewell rather than a shout, these stars teach us that endings come in many forms. Sometimes, the most profound transitions happen not with resistance, but with acceptance of the natural flow toward new states of being. In the cold spaces between stars, Molecules form from the breath of stellar endings. The Atacama Large Millimeter Array has detected complex molecular emission from supernova ejecta, revealing chemistry in action amid cooling stellar remnants. Carbon, oxygen, silicon, and other elements, scattered by the explosion, find each other in the vacuum, forming the first simple compounds. From these humble beginnings arise the molecular complexity that eventually leads to planets and life. We are the distant descendants of this cosmic chemistry, our existence built upon molecular foundations, first formed in the cooling aftermath of ancient stars. Their ending breaths became the first whispers of the chemistry that would one day form you. Some stars wrap themselves in helium veils before their final performance. Many type Eben supernovas show evidence of interaction between explosion ejecta and helium-rich material the star released before its death. This stellar farewell creates distinctive spectral lines as the shockwave illuminates the surrounding cocoon. There is poignancy in these final preparations, as if the star adorned itself before its transformation, creating beauty that would only be visible after it was gone. How often do we only see the meaning of someone's actions after they've departed? These stellar farewells remind us that what we leave behind continues to shape the light others will see. The ripples in space-time may soon reveal the hidden heartbeats of dying stars. Gravitational wave detectors may eventually observe the collapse phase of nearby core collapse supernovas, sensing distortions in space itself as stellar cores implode. These waves travel unimpeded through matter, carrying information from moments no light can escape. Unlike electromagnetic radiation, which takes hours to emerge from the stellar interior, gravitational waves offer a direct window into the birth of a neutron star or black hole. We stand at the threshold of perception, learning to feel the universe through its subtle vibrations. In our quest to understand, we extend our senses beyond light into the very fabric of space. Before their final transformation, some stars shed brilliant tears that linger as memory. Many supernova progenitors undergo luminous blue variable eruptions, releasing shells of material that create complex environments surrounding the star. Years or centuries later, when the core finally collapses, the explosion illuminates these concentric layers of stellar history. Each eruption marks a phase of the star's life, preserved in expanding shells of matter. We too leave impressions of our different seasons around us, in relationships, in created things, in memories held by others. Like stars, our presence continues in what we've shared, even after our brightest moments have passed. Our cosmic cartography grows more precise with each passing year. The Gaia Space Telescope will measure accurate distances to nearby supernova remnants using stellar parallax, observing how stars appear to shift against the background as Earth orbits the Sun. This ancient technique, refined with modern precision, creates three-dimensional maps of these stellar remains. There is something deeply human in this patient measurement, this need to understand exactly where things are in relation to ourselves. We map our cosmos as our ancestors mapped their lands and seas, finding comfort in knowing our place amid vastness, connecting to remnants of stars long vanished through the simple act of measuring the space between. The stories of stars are often written by their companions. Many stripped envelope supernovas originate from systems where a companion star pulled away the outer hydrogen layers of the progenitor before its collapse. This cosmic relationship fundamentally changes how the star will end, creating distinctive spectral signatures when the core finally collapses. We are similarly shaped by our relationships, our trajectories altered by connections with others. The universe shows us that even stars do not evolve in isolation, but through exchange and interaction. Their light carries evidence of these shared histories, these cosmic partnerships that transformed them before their final moments. A star's life story is written in the gentle breath of stellar winds. The pre-supernova evolution of massive stars depends critically on mass loss rates and metallicity, how much material they exhale into space throughout their lives, and the abundance of elements heavier than helium in their composition. These factors determine their final structure before collapse and the nature of their explosion. Like us, stars are shaped by what they release and what they contain, their endings influenced by lifetime patterns of giving and holding. The cosmos teaches us that letting go is not just an ending, but a continuous process, preparing the way for the transformations that await us all. Long after stars vanish, their remnants may find each other in cosmic embrace. Some kilonova events occur when neutron stars, dense cores left by supernovas, merge after orbiting each other for millions of years. These rare collisions create flashes of light and gravitational waves, while forging the heaviest elements in the universe. There is profound patience in this process, stellar cores circling through eons before their final encounter. We witness the completion of stories that began in ancient supernovas, reminding us that endings often contain beginnings. What appears complete may simply be paused, waiting for the right moment to continue its transformation. Our vision extends deeper into stellar ghosts with each generation of cosmic eyes. The European Extremely Large Telescope will resolve individual supernova shock fronts in nearby galaxies, revealing details previously hidden by distance. These massive instruments represent our collective desire to witness and understand cosmic processes. There is wonder in this shared endeavor. Thousands of people designing, building, and operating these telescopes so we can better see our place in the universe. We extend our perception through cooperation, creating technologies that let us witness stellar endings across millions of light years, connecting human curiosity to the grand cycles of cosmic transformation. Some stellar endings remain hidden from our sight, like whispered secrets in the cosmic dark. Many supernova remnants in the galactic plane lie concealed behind dust clouds and molecular gas, invisible to optical telescopes. Only radio waves and X-rays penetrate these veils, revealing the shapes of ancient explosions. There is humility in recognizing how much remains hidden from us, how the universe preserves some mysteries despite our best efforts to see. We learn to look differently, to sense through other wavelengths, finding beauty in what was previously unseen. Sometimes understanding requires us to move beyond our natural senses into new ways of perceiving. The first messengers of stellar transformation travel in whispers we're only beginning to hear. The neutrino signal from a galactic supernova would arrive hours before any visible brightening, carrying news of the core's collapse before light escapes the star's dense interior. These nearly massless particles stream through matter almost without interaction, reaching us directly from the heart of transformation. We are learning to listen for these subtle voices, to receive the earliest news of cosmic change. In their patient journey through the star and space, neutrinos remind us that the quietest messages often carry the most fundamental truths about our universe. Not every stellar ending fulfills its cosmic promise. Some Type A IAX supernovas may represent failed explosions of white dwarf stars, partial detonations that leave behind remnants rather than complete destruction. These less-than-complete transformations create distinctive light patterns that astronomers can recognize across vast distances. There is compassion in acknowledging these partial endings, these transformations that don't follow expected paths. The universe embraces variation, allowing for many kinds of transitions beyond simple categories of success or failure. Perhaps these stellar remnants remind us that transformation itself, in whatever form it takes, is what continues the cosmic story. Our quest to witness cosmic endings extends to the farthest reaches of space and time. The 30-meter telescope will study supernova progenitors in distant galaxy clusters, observing stars that lived billions of years ago in environments different from our own. Through these observations, we trace how stellar endings have changed throughout cosmic history. There is profound connection in this backward gaze, our present moment reaching toward ancient light, learning how stars lived and died when the universe was young. We are the cosmos grown aware of its own history, seeking patterns that connect stellar generations across the vast ocean of time. Stars sometimes remove their outer layers before their final performance. Many Wolf-Rayet stars represent the final evolutionary stage before core collapse, supernovas, their intense stellar winds having stripped away their hydrogen envelopes to reveal hot, luminous cores. These stars shine with extraordinary brightness while rapidly losing mass to space. There is vulnerability in this unveiled existence, the star's innermost nature exposed before its final transformation. Like a butterfly emerging from its chrysalis shortly before the end of its life, these stars remind us that revealing our essential nature may be the prelude to our most profound transitions. Our understanding of the expanding universe rests on the light of dying stars. The Dark Energy Survey has discovered thousands of supernovas for cosmological distance measurements, using their consistent brightness to map the universe's accelerating expansion. These stellar endings become cosmic tools, helping us comprehend the vast spaces between galaxies and the mysterious forces shaping our universe. There is poetry in how we find meaning in endings, how the brief flashes of stellar transformations illuminate our widest questions about existence. Through patient observation of countless stellar farewells, we glimpse the universe's future and our place within its continuing story. Not every stellar explosion leaves nothing behind. Some thermonuclear supernovas may leave behind bound remnants rather than completely disrupting their progenitor stars. These surviving fragments, perhaps still orbiting companion stars, carry memories of the explosion that transformed them. Astronomers search for these rare survivors, hoping to better understand the explosion mechanisms. We find comfort in this continuity, this evidence that even cosmic catastrophes can leave something preserved. Like forests that regrow after fire, or communities that rebuild after disaster, these stellar remnants remind us that endings often contain seeds of continuation. The fabric of space-time itself will whisper news of stellar collapse to our waiting instruments. The laser interferometer, space antenna, will detect gravitational waves from supernova core collapse, ripples in space that travel unimpeded by dust or gas. These waves carry information about the symmetry of the collapse and the birth of neutron stars or black holes. There is wonder in our growing ability to sense the universe beyond light, to feel its vibrations and hear its rhythmic transformations. We extend our perception into the fundamental nature of space and time, connecting human consciousness to the subtle language of gravity itself. In the heart of dying stars, turbulence prepares the way for transformation. Many carbon-oxygen white dwarfs undergo convective carbon burning, before thermonuclear runaway, mixing and heating that set the stage for explosion. This internal stirring determines how the flame will propagate through the star, shaping its final moments. We recognize this pattern of preparation before change, this gathering of energy before release. The universe shows us that transformation often begins with internal movement, with the rearrangement of what was stable into new patterns with new potential. Our own periods of inner turbulence may similarly prepare us for necessary change. Each night, cosmic detectives discover the fleeting light of stellar endings. The Zwicky Transient Facility discovers approximately 2,000 supernovas per year, systematically scanning the sky for changes and alerting astronomers to new cosmic explosions. This patient vigilance ensures that few nearby stellar deaths go unnoticed or unstudied. There is dedication in this continuous attention, this refusal to let significant moments pass unwitnessed. We honor transitions through observation, through being present at thresholds. Like friends gathering to mark important passages, astronomers around the world coordinate their instruments when a new supernova appears in our skies. The first generation of stars died in ways we can only imagine. Some population 3 stars in the early universe may have undergone pair instability supernovas, complete disruptions that scattered their elemental creations without leaving remnants. These ancient explosions seeded the pristine cosmos with the first heavy elements, beginning the enrichment that would eventually enable planets and life. There is ancestry in this primordial seeding. Our existence traces back to these first stellar endings before galaxies had fully formed. We are descendants of cosmic pioneers whose transformations prepared the way for all the complexity that would follow. Our cosmic census of stellar endings grows more complete with each passing year. The Roman Space Telescope will conduct the largest supernova survey in astronomical history, discovering hundreds of thousands of these cosmic explosions across vast distances and cosmic time. This unprecedented sample will reveal patterns previously hidden by limited observations. There is patience in this gathering of evidence, this careful documentation of how stars complete their stories across the universe. We find meaning in the accumulation of many individual endings, seeing how they collectively shape galaxies and create conditions for new beginnings. Some stars end their stories with extraordinary speed. Many type IKBL supernovas show broad absorption lines indicating high-velocity ejecta, material expelled at substantial fractions of light speed. These rapid expansions may connect to gamma-ray bursts, the most energetic explosions in the universe. The star's final moment unfolds with unexpected intensity, its energy concentrated into jets that briefly outshine entire galaxies. We witness cosmic extremes in these rare events, reminders of the universe's capacity for transformative power. Like lightning that momentarily outshines the sun, these stellar endings demonstrate how a single moment can release energy accumulated over millions of years. The birth cries of neutron stars will soon reach our waiting ears. The advanced LIGO detectors will observe gravitational waves from rotating supernova cores, asymmetries in collapse that send ripples through space-time. These waves carry information about how stellar cores transform into neutron stars, revealing processes hidden from electromagnetic observations. There is connection in this new perception. Our instruments, feeling the subtle squeeze and stretch of space itself as stars undergo their most profound transitions. We become witness to cosmic births that follow cosmic deaths, the universe sharing its most intimate moments with conscious observers. Even stars below the expected threshold sometimes find their way to transformation, Some sub-Chandrasekhar mass white dwarfs may explode through helium detonation mechanisms, the fusion of accumulated helium triggering carbon burning despite the star's lower mass. These unexpected explosions remind us that thresholds are rarely absolute. The transformation finds many paths. We see reflections of our own experiences in these stellar surprises. How change sometimes arrives before we thought ourselves ready. How catalysts can trigger transitions that seemed unlikely or impossible. The cosmos embraces exceptions alongside patterns, welcoming diversity in how endings unfold. A new window opens onto the cosmic landscape of stellar transitions. The Vera Rubin Observatory will revolutionize supernova science through its 10-year survey, creating a movie of the changing night sky with unprecedented depth and breadth. This cosmic cinema will capture thousands of supernovas each night, tracking their evolution and revealing connections previously hidden by limited observations. There is celebration in this shared endeavor, this global collaboration to witness and understand. We join together across continents and cultures, focusing our collective attention on the rhythms of stellar lives and deaths that form the heartbeat of our universe. Some stellar remnants reach their endings through quantum surrender rather than gravitational collapse. Many oxygen neon magnesium white dwarfs undergo electron capture collapse at 1.37 solar masses, their electrons merging with atomic nuclei when densities reach critical thresholds. This process triggers implosion without the violence of iron core collapse in massive stars. There is elegance in this quantum transition, this gentle acceptance of physical law. Like ice transforming to water, when temperature reaches a precise point, these stars demonstrate how nature's thresholds guide cosmic transitions. Their quiet transformations remind us that profound change need not always arrive with dramatic display. Our vision continues to sharpen, revealing stellar details once thought forever hidden. The Event Horizon telescope techniques may eventually image supernova shock fronts using coordinated observations from telescopes across Earth to achieve resolution impossible for any single instrument. This planetary collaboration overcomes fundamental limitations, allowing us to see finer details across vast distances. We transcend our individual perspectives through cooperation, creating a collective eye that sees what no individual could witness alone. In joining our instruments and minds together, we extend human perception to touch cosmic events with unprecedented clarity. Stellar cores spinning in magnetic embrace create cosmic beacons that pulse across space. Some magnetorotational supernovas may explain the origin of highly magnetized neutron stars, their cores spinning rapidly during collapse, amplifying magnetic fields to extraordinary strengths. These fields channel energy and shape the explosion, leaving behind pulsars that sweep beams of radiation through space like celestial lighthouses. We find wonder in how rotation and magnetism intertwine during transformation, creating order within catastrophe. Like dancers finding balance in motion, these stellar cores demonstrate how dynamic forces create enduring patterns even in moments of profound change. Our vision extends beyond visible light into the hidden warmth of cosmic transitions. The next generation of space-based telescopes will observe supernovas in the infrared with unprecedented sensitivity, revealing details obscured by dust and distance. These observations will show us how stars end their stories in the earliest galaxies, connecting present understanding to cosmic dawn. There is continuity in this extended perception, our instruments reaching across wavelengths and time to witness how stellar endings have shaped universal evolution. We extend our senses beyond natural limitations, touching cosmic history through technological windows that reveal the universe's long, ongoing transformation. Within stellar remnants, we find natural laboratories for understanding the fundamental nature of matter. Many supernova remnants provide environments for studying plasma physics under extreme conditions, temperatures and densities impossible to recreate on Earth. These cosmic experiments reveal how magnetic fields form and evolve, how shock waves propagate through interstellar gas, and how particles accelerate to nearly the speed of light. We learn universal principles from these stellar aftermaths, finding patterns that apply from quantum scales to cosmic distances. In their expansion and evolution, these remnants continue teaching long after the star's transformation, offering lessons about the physics that shapes our reality. As the light of distant explosions fades into the dark velvet of your mind, our journey through the cosmic spectacle of supernovas draws to a close. We've witnessed the elegant dance of electron captures, explored hidden remnants behind cosmic veils, and contemplated waves of gravity rippling through the fabric of space itself. From the ancient enrichment of globular clusters to the future promises of the Vera Rubin Observatory, we've traveled across time and space to understand these magnificent stellar farewells. You are made of supernova dust, the calcium in your bones, the iron in your blood, all forged in the tremendous heat of these stellar explosions. As you rest tonight, remember that your very existence connects you to the most powerful events in our universe. These celestial phenomena that scatter elements across galaxies have, in their own way, helped create you. As your consciousness drifts, the universe continues its patient work. Somewhere, a massive star is entering its final moments. Somewhere else, the light from an ancient explosion is still traveling toward Earth. The cosmos doesn't rush, and neither should you as you settle into peaceful sleep. If you're still awake and your mind craves more cosmic lullabies, our channel has many more soothing scientific journeys waiting for you. But for now, may your dreams be as vast and beautiful as the supernova remnants scattered across our night sky. Good night.